Now, in order to study the non-homogeneous differential equation and learn how to solve it, we need a couple of theorems here. So we're going to introduce our first theorems of the semester. If y sub h of t, we're just using that subscript of h to distinguish it from another function. So the sub h has very little importance at the moment. But if yh is a solution to a homogeneous ODE, that's homogeneous, that's why we use the h there, then so is any constant multiple of the solution, k times y sub h of t, where k is just any real number. And typically, and ideally, that's going to be a non-zero real number. So it could be a fraction, decimal, but the second you put a zero out there, it becomes a pretty boring solution. You get the trivial solution. So first of all, let's show that y sub h of t is a solution of dy dt equals y. Then show that any multiple of that is also a solution. So if y sub h of t is e to the t, in order to verify that it's a solution, I've got to check, does its derivative equal itself? And so if I take the derivative, y prime of h of t, y sub h, then I get, well, the derivative of e to the t is e to the t. Now when I substitute in the derivative of that solution, which is e to the t, and I substitute in the function, which is e to the t, are they equal? Yes, they are. Therefore, e to the t is a solution. Now again, the y sub h is just used to denote that it's a solution to a homogeneous differential equation. So don't let that throw you off. That's just, soon we'll see that it doesn't have to be a solution to a homogeneous case. And show also that k times y sub h of t is also a solution. So if y sub h of t is e to the t, then if we multiply that by k, then k y sub h is k e to the t. So the derivative of that, the derivative of k times y sub h, the prime of that is the derivative of this function, which is simply equal to, well, the derivative of k e to the t is k e to the t. The coefficient out front doesn't make a difference. And now we just need to check, does dy dt equal the original function? Well, they are the same, right? So if I plug in k e to the t for the derivative of that, and the function that I took the derivative of was also k e to the t, they are in fact equal to each other. So once again, I've just shown that since this is a solution, so is any multiple of that solution. Now let's just do a general proof here, because we've verified it for one specific differential equation, but I don't want you to be afraid of convincing yourself that something is mathematically true. And how do you verify something? So the theorem says that as long as you know, the condition is that y sub h is a solution to a homogeneous ODE. So what we're going to need to verify is, first of all, let's focus on the first order linear differential equation. So first of all, we'll say something like this. Well, the condition is that you found a solution, right? So first of all, suppose y sub h is a solution to dy dt equals a of t times y. So that's the first order linear differential equation. Notice that I have a plus 0 here. That's my homogeneous case of this equation. And so as long as this equation is homogeneous, this means that if I were to take the derivative of y sub h, that would in fact equal a of t times y sub h. So that's what that means. So all I've done here in practice is I've used the condition from the first step, which basically said that suppose it is a solution. Well, if it is a solution, that means I should be able to plug in its derivative on the left, the function on the right, and I should get the two sides to be equal to each other. So this is a true equality here. So if that's the case, let's now check or construct the solution, or construct equality for k sub h, or k times y sub h. So if all I were to do here is the derivative of k y sub h, the derivative of that with respect to t, right? Now this is literally another way you could write dy dt is it's the derivative of this function with respect to t. So if I have the derivative of a constant multiple of something, that means I can factor it out. So k times the derivative with respect to t of y sub h. Okay? And now I know that the derivative of y sub h with respect to t, I know that this whole thing by equality is equal to this whole thing. So this leaves me with k times a of t times y sub h. Now because I have the multiplication of three things here, I can rearrange the order in which I multiply those things. And if I write it like this, you can in fact see that from our equalities here, from our three equalities, what we're now able to deduce is that the two ends are equal to each other, right? Because I have a bunch of equal signs here, and so ultimately, since these things are all equal, it follows that the derivative of k times y sub h is equal to a of t times k times y sub h. And so notice that this and this are identical, and that basically this k times y sub h satisfies the differential equation. So if in our equation I had replaced y sub h with k times y sub h, the equality still works out. And for that reason, this multiple of y sub h is also a solution. Now, this linearity principle has an extension, and that extension says, given the non-homogeneous ODE, dy dt equals a of ty plus b of t, and its associated homogeneous reduction. So even though the equation that you have may not be homogeneous, if you omitted that b of t term and just left it as plus 0, if you literally reduced it down to deleting that, and you found a homogeneous solution, y sub h, as the general solution to the homogeneous reduction equation, and you found some particular solution to the non-homogeneous equation, then the general solution is we could take those two solutions and add them together, and that would form the general solution to the non-homogeneous case. Now that doesn't seem like it helped us at all, because even though we know how to solve the homogeneous equation by using separation of variables, to find this particular solution to the non-homogeneous case seems like it just puts us back at the start, but we've already done a lot of work. Before we get into how we would actually find y sub p, that's the thing that we're going to be after, let's just go ahead and see that this theorem actually works. So show that y sub h and y sub p are solutions of the homogeneous reduction and non-homogeneous equation dy dt equals negative 4y plus 3e to the negative t. So the homogeneous reduction of that would just say omit the 3e to the negative t term. Here's my a of t, here's my y. So let's just focus on this equation right here. Now I just need to check that y sub h, this guy here, I just need to check that that satisfies this equation. So I need to make sure that the derivative of this guy, that the y prime of h, okay, so that's going to be, the derivative of that will be negative 4k e to the negative 4t. Y sub h, of course, is just k e to the negative 4t. And if I now plug those two equations in, or those two functions in, for the left and for the right, the derivative, negative 4k e to the negative 4t, I want to see, does that equal negative 4 times y? Well, y is k e to the negative 4t. And if I just remove the parentheses, you see that, in fact, these two sides are equal, and therefore y sub h is a solution to the homogeneous reduction. Now we want to show that y sub p of t is a solution to the non-homogeneous case. So now I just want to check, does y sub p satisfy this equation right here. And in order to do that, I have to look at y sub p. So y sub p is the equation e to the negative t. Its derivative is negative e to the negative t. And now what I need to do is just plug in y prime up here, plug in y sub p in here, and see if the two sides are equal. So does negative e to the negative t, question mark, equal negative 4 times e to the negative t plus 3 times e to the negative t. So on the left I see that I have, or on the right I see I have negative 4 e to the negative t plus 3 copies of e to the negative t. That actually gives me negative 1 copies of e to the negative t. And the left-hand side, there's nothing to reduce, but I do see that they're equal to each other. Finally, it says, show that the sum of these is also a solution. So in order to do that, what I'm going to have to do is I'm going to have to now look at the general solution, which is y equals the sum of the two functions. So the homogeneous is k e to the negative 4t. If I add to that the non-homogeneous, the y sub p, which is e to the negative t, I want to check, is this a solution of dy dt equals negative 4y plus 3e to the negative t. Okay, so what I'm going to do to verify this is, first of all, I need the derivative of this guy. So the derivative of what I'm claiming to be the general solution is negative 4k e to the negative 4t. And then the derivative of e to the negative t is negative e to the negative t. And now if I come over here and I plug in y prime for dy dt, and I plug in y for negative 4y, then on the left-hand side I will have negative 4k e to the negative 4t minus e to the negative t. So I've just replaced dy dt with the derivative of y. And now I want to check, is that equal to negative 4 times the y function, which is k e to the negative 4t plus e to the negative t, and then add on the end of it the result. So this piece here is just our substitution for y plus 3e to the negative t. So first of all, I'm going to see that when I distribute this, here I'll get negative 4k e to the negative 4t. Now when I distribute it here, I'll get negative 4e to the negative t, but then I'm going to be adding positive 3e to the negative t to it, so this will leave me with negative e to the negative t, and check it out. The two sides are, in fact, equal to each other. Therefore, I have proven that the particular solution, which is e to the negative t to the non-homogeneous case, added to the solution for the homogeneous reduction, forms a solution that's general for the entire differential equation. Let's see that this works. So suppose that y sub h of t is a solution to the homogeneous reduction, and that y sub p of t is a solution to the non-homogeneous case. So we start off the proof by saying that. So if that's true, then I want to check, is y equals y sub h plus y sub p, is that a solution? Well, if I want to verify that it's a solution to this non-homogeneous case, then I'm going to need its derivative as well. And the best I can do is I can just write this as y prime of h, or I could write, so I can write y prime sub h plus y prime sub p. Now, since we don't know what functions they are, all we can say is that, well, the derivative of y sub h is y prime of h. The derivative of y sub p is y prime of p. And so now, if I want to verify that it's a solution to dy dt equals a of ty plus b of t, what I need to do is show that the two sides are equal to each other. So the derivative of y, that's going to be y prime of h, or I'm going to write it as dy h dt. and y prime of p I'll write as dyp dt. And does that question mark equal a of t times y? Well, y is y sub h plus y sub p, and then plus my b of t term here. Now, this becomes sort of an algebraic argument. When I distribute this, I'll have a of ty sub h plus a of t y sub p plus b of t. And I want to see if these two sides are equal, but there's not much algebra to go off of here. The only thing that I'm allowed to use is the fact that I know from the suppose that y sub h is a solution to this. So notice that what I have here is y sub h, the derivative of y sub h. Well, what I know that that's equal to is a of t times y sub h, because I know that y sub h is a solution to that homogeneous reduction. I also know that y sub p, its derivative, better be equal to a of t y sub p plus b of t. So the green is equal to the green, the purple is equal to the purple, and therefore these two sides are equal to each other because the green plus the purple equals the green plus the purple, for a lack of mathematical speak. All right, so there's kind of some algebraic proofery, so for a lack of better terms, some mathematical proof for why this theorem works. So a lot of times when we're proving something, we're using general arguments. We're trying to show that things are equal to each other, and we have to do so with limited knowledge about what those functions might be. Of course, we can prove it for specific examples, but theorems aren't very good if they are just for specific examples. We need them to be good for any function that we deal with.